Hey everyone, welcome back for more AP Calculus. Today we're going to be looking at section 8.3, and this is where we start looking at volume of solids formed by revolution of a region. This is one of the cornerstones, basically the ending point where you would be in the calculus AB, sorry, not BC, calculus AB. And in BC, it's still in their curriculum, but it's a little bit less emphasized than it used to be. As a note, at the very end here, we're going to be looking at solids formed using the cylindrical shell method, which strictly speaking isn't on the AP exam, but it is something that a lot of AP Calculus teaches, especially if you're going to take calculus in college. So it's optional, and you can, of course, stop anytime you like, especially there if you don't want to look at the end there. But also, remember that you can pause anytime you like and work on the problems. And let's get started. Okay, so we start off with a little bit of conceptual stuff. The volume of a solid, if you will remember, it's going to be basically the area or the volume of a bunch of really thin prisms or cylinders in the case of rotations, all kind of stacked up together. And when you add up all of those small volumes, you get a volume of a whole solid. And the process by which we add all of those volumes together is this integration. So integration is, one way to look at it is just another fancy way of adding a bunch of stuff together. Now we're saying that these are prisms or cylinders, and when you look at it and you approach it as a prism or a cylinder, then the height of that cylinder, the very small slices, that is going to be either a dy or a dx. Find the volume of the region generated by revolving the graph of y equals f of x, the x-axis, and the lines x equals a and x equals b are about the x-axis. Each slice has the shape of a circle whose radius is f of x. So just as a note, whenever you're revolving around an axis, your cross-section is guaranteed to be a circle. That's what happens when you revolve things, you get a circle. So the area of the circle is going to be pi multiplied by the f of x squared. And so the volume of each cylinder is pi f of x squared, where the volume of the entire solid, all those cylinders stacked up together, would be an integral of that pi times f of x squared. Now this is the disk method. This doesn't, well, it applies, but it's not exactly the same thing as if each of those cross sections had a hole in it. That's what we call the washer method, and I'm sure we'll be looking at that in a minute. So again, note, all the cross sections are circles, so the area of each cross section is pi r squared. And so the volume of each cross section is pi r squared dx. So suppose we have the base of a solid is that shaded region that you see there. It's a semicircle, or at least it appears to be a semicircle. And all the cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So this is a little bit different because we're not revolving around an axis. We're saying each cross section is a square. So you can see there at the bottom we have one slice here is a square, and the thickness of each of those squares is at dx. F of x is a height that's from the top of the square to the bottom of the square. And you can see that on the base of the solid with this lighter colored square. This lighter colored square is meant to be this square right here. So note the cross sections are squared. So the area is equal to s squared, where s is just f of x minus 0. I like to emphasize here that the side or the length or whatever the footprint of that object that you're looking at, that's always going to be a difference of two functions. Now, if one of those functions is the x-axis, then that's how we get the f of x minus 0. So this brings us to a few problems. Number 1, you've got the region bound by f of x equals x squared right over here, the x-axis right down here, and x equals 2 right over there. And we're going to revolve that, rotate that region about the x-axis. So the first thing is to draw that solid of revolution. When I was taking calculus, we spent a lot of time drawing these solids of revolutions. Well, here's my solid of revolution right over there. As you can tell, this kind of looks like a funnel. Actually, it kind of reminds me of those gravitational things you would see at the Griffith Observatory, but that's probably a really specific example. Okay, so that's our graph. We'll draw and label a slice. Well, our slice would basically be that red line that you see over here. And then that red line, of course, when you rotate it, that's going to be a whole disk. B, draw and label a slice. Let's draw that slice. Of course, the slice is a circle. Notice right over here in red, right in the center of that circle or disk, that's the x-axis. And f of x would be the distance from the x-axis up to that curve. So we're looking at the radius is f of x minus 0. You'll notice that we have this right here in red. That's the same thing as this blue section here. Sorry I didn't get a chance to color coordinate that. But this blue line here, the radius, is the same as this line over here. So let's find the area of the cross section of the solid. If you know you're rotating around an axis and you know the cross section is going to be a circle, and the area of a circle is always going to be pi r squared. And we just found out that r is equal to f of x minus 0. So r is equal to x squared, meaning that we have an area of actually pi x to the 4th power. So here's pi r squared. I think I forgot a square here. Okay then, so for the volume of one slice, that's pi r squared times dx. So that gets us to pi r squared dx. And if you simplify that, that looks like pi times x to the 4th delta x, which of course is going to become our dx. Okay, so the volume of the solid as an integral, well, you're just going to integrate all of those slices together. So it's an integral from 0 to 2 of pi x to the 4th dx. And now comes the job of actually integrating. Pi is constant. The antiderivative of x to the 4th is 1/5 x to the 5th power. And when you substitute 2, you get 32 pi over 5, or, 32 pi over 5 minus 0. But of course, 0 is what it is, so we don't need to write it there. Okay, so let's revolve something around a vertical axis. Here we have a region bound by f of x equals x squared, the x-axis, and x equals 2, and now we're going to rotate it about the y-axis. Actually, this is the exact same region, isn't it? Okay, so draw the solid of revolution. I always start by reflecting it, the region about the axis of revolution, and then I connect things with semicircles. So here's what we got. Here's what it looks like. Notice it kind of looks like a hollowed out, kind of like a bowl, really. All right, and the cross section. This time our cross section looks like a washer, because there is, if you will notice, the axis of rotation is not one of the boundary curves of the region. So whenever that happens, if the boundary curve is not a boundary of the region, then you're going to create a washer. So we know that the cross sections are going to be washers. So if you want to find the area of a washer, it's basically the area of one circle, the outer circle, minus the area of the inner circle. So that's what we're going to do when we find the area of the cross section. That's just going to be the area of 1 pi r squared minus another pi r squared. And with this method, of course, we really have to make a distinction between which is the outer radius and which is the inner radius. So if you take a look at the diagram over here, notice the outer radius here goes all the way to x equals 2. And that's this large capital R over here. This is x equals 2. This inner radius goes all the way to basically the part of the curve that's closest to the axis of rotation. So if f of x equals y, that means y equals x squared. So y equals x squared. So that means that any x coordinate can be given by the square root of its y coordinate. And the small radius is any curve along this y equals x squared. So the x coordinate at any point along that curve is the square root of y, which of course is the radius. So the volume of one slice is going to be pi r squared minus pi r squared multiplied by delta y. And then the volume would be the integral of that same expression, which appears backwards. That looks better. Integrate, and this integral is not that difficult again. So it's 4 pi y, minus 1/2 pi y squared, which when you substitute everything, you get an 8 pi. Okay, so how are we feeling so far? Remember, all we're doing is just integrating area formulas. So when we get to this, number 3, again, you're just going to be integrating an area formula. So you got to look out for what is the area formula. So we have the base of a solid is bound by x plus 2y equals 4. And the coordinate axes, that's the x-axis and the y-axis. Each cross-section slice is made perpendicular to the y-axis is an isosceles right triangle with a hypotenuse on the base. So that's a lot of information. Let's take a look at what this region looks like. Okay, so here's the base of the solid. Graphing that, and notice that in red here we have the, what are we calling this? The slice made perpendicular to the y-axis in red. So since it is perpendicular to the y-axis, the length of that red slice is going to be a difference in x-coordinates. So if you look at that, the x-coordinate here, right along that curve, or the line in this case, the x-coordinate there is 4 minus 2y, given by this equation up here. And over here on this side, on the left side of the region, that x-coordinate is always equal to 0. So part B, let's draw and label one slice. Here's our slice. Notice that this red segment over here is the same thing as this red segment right here is the same thing as this red segment right here. And how long is that red segment? That's 4 minus 2y minus 0, which we just discussed. And so if you want to find an area for this cross section, knowing that this is a right angle, well, the area of this cross section is 1/2 s squared. Well, how much is s squared? Using the Pythagorean theorem, we know that s squared plus s squared is equal to 4 minus 2y squared, which is this equation right here, which means that s squared is 1/2 of 4 minus 2y squared. Now, you're probably tempted to solve for s at this point, but that's kind of unnecessary because the area formula is in terms of s squared. So if the area formula is 1/2 s squared, then the area is 1/2 of 4 minus y squared. And the area of the cross section, therefore, is 1/4 of 4 minus 2y squared. So we're going to do some cute algebra here. From this inner parenthesis, we're going to factor out a 4. And that 4 is this 2 squared. I'm sorry, we're going to factor out a 2. And of course, if we're going to factor out a 2, then it's going to be squared as well. So we're factoring out a 2 squared, and that's where this comes from. And then 2 squared and that 1/4 simplify. And the area formula is just s minus y squared. Okay, so that's some algebra work, but let's continue on with the calculus stuff here. Find the volume of one slice. Well, that's just the area formula multiplied by delta y. And then if you want to find the volume, you're going to integrate the areas of the slices. Our delta y becomes a dy. And this antiderivative is not that difficult. Here we did some substitution rule. If you wanted to expand this and then just use polynomial rules, that's fine too. Substitute a 2 here and you get 0. Substitute a 0 here and you get 8/3. So the area or the volume of the solid is 8/3. Now remember, the cross sections were not circles. There were no circles anywhere in this problem. That's how come you don't see a pi. I can't tell you how many times I see students putting in a pi for every area, every volume problem, and it's kind of nauseating, to tell you the truth. So you got to take a look. What is the area? What is the volume? If it involves a circle, then you would expect to see a pi. If it doesn't involve a circle, then there's no reason to have a pi anywhere. So that's really the end of our volumes of cross sections and rotations. This next little bit is an optional part of Calculus BC, and it's going to be the cylindrical shell method, and we're going to take a really quick look at it. If you want to stop the video here, awesome. If not, let's move on. So here is what we do with what we call the cylindrical shell method. So the method of computing a volume by cylindrical shells may seem really different, but it's actually kind of the same process. Generally speaking, we're going to add a bunch of areas together, but instead of areas being flat pieces, the areas are going to be kind of like tree rings. So if that makes sense to you, take a look at figure 2 here. Here is one cylindrical shell. If we cut that cylindrical shell apart, you get basically a rectangle. So again, imagine if this is made out of paper and you took a pair of scissors and you went all the way down this shell and you unrolled it, you would get a piece of paper. So how tall would this piece of paper be? Well, when we go back here, the height of the piece of paper was from here to here, or that's the height of the shell. And what that basically is this top function minus the bottom function again. Top function minus bottom function, which is f of x minus 0 in this particular case. How about L? The length of this, what would that be? Well, coming back to figure 2, the length of that would have been the circumference of this shell. And the circumference of that shell is kind of dependent upon where this shell stacks up. Okay, how far from the axis of rotation is it? So for this one, the length, the radius of this shell is going to be the x-coordinate minus the axis of rotation. So the length of this cross-section, shell cross-section, that's going to be 2 pi x. Notice that the radius is x minus the axis of rotation, which in our case is just equal to x. So L is 2 pi x. Okay, still with me? Let's keep going. W in terms of f of x, well, no, we already did those two. Sorry. We're on letter C now. So the face area, the area of that shell is L times W. Well, we already have L times W. And when we multiply that out, we get 2 pi x f of x. Okay. So if you want to find the volume, all you got to do is integrate all those area formulas. Remember I said that the two methods were really similar, and they're both similar because we're still integrating an area formula. So let's integrate that area, the volume of the one shell is 2 pi x f of x dx. And then when you integrate it, you get the volume of the entire thing. So that's it, everyone. Hopefully you understand the process, or you've reviewed the process of finding the area or the volume of cross sections, either by rotation or by slicing. And we'll see you next time.